In the last lesson, we proved that u of t convolved with u of t equals r of t. Now let's extend this to shifted steps. Consider u of t convolved with u of t minus 2. Setting up the integral, u of tau is 1 for tau greater than or equal to 0, and u of t minus tau minus 2 is 1 when tau is less than or equal to t minus 2. The overlap is from 0 to t minus 2, so the integral equals t minus 2, valid for t greater than or equal to 2. Therefore, u of t convolved with u of t minus 2 equals t minus 2 times u of t minus 2, which is r of t minus 2. Similarly, u of t minus 2 convolved with u of t minus 3. The overlap is from 2 to t minus 3, giving t minus 5 for t greater than or equal to 5. So u of t minus 2 convolved with u of t minus 3 equals r of t minus 5. Notice the pattern. When we convolve two shifted unit steps, the shift values simply add up. In general, for a greater than 0 and b greater than 0, u of t minus a convolved with u of t minus b equals r of t minus the quantity a plus b. The two delays add, and the result is always a ramp function. This powerful shortcut lets us compute step convolutions instantly without setting up any integrals. Now let's learn graphical convolution, a visual method for convolving any CT signals. Consider x of t, a rectangular pulse of height 1, from t equals -1 to t equals 1, and y of t, a rectangular pulse of height 1, from t equals 0 to t equals 1. To compute the convolution integral, we first replace t with tau in both signals. Then we flip y of tau about the origin to get y of negative tau, which is a pulse from -1 to 0. Finally, we shift this flipped copy by t to get y of t minus tau, a pulse from t minus 1 to t. Now we slide y of t minus tau across x of tau and compute the overlap area at each position. When t is less than -1, there is no overlap, so z of t equals 0. When t is between -1 and 0, the sliding pulse partially overlaps x of tau. The overlap width is t plus 1, so z of t equals t plus 1. When t is between 0 and 1, the pulse fits entirely inside x of tau, giving full overlap of width 1, so z of t equals 1. When t is between 1 and 2, the pulse starts sliding out from the right. The overlap width is 2 minus t, so z of t equals 2 minus t. Finally, when t is greater than or equal to 2, there is no overlap again, and z of t equals 0. The result z of t is a trapezoid. It rises linearly from 0 to 1 between t equals -1 and 0, stays flat at 1 between 0 and 1, then drops linearly back to 0 between 1 and 2. This is the piecewise formula. 0 for t less than -1, t plus 1 for -1 to 0, 1 for 0 to 1, 2 minus t for 1 to 2, and 0 for t greater than 2. There's also an algebraic approach. We write both signals in terms of unit steps. X of t equals u of t plus 1 minus u of t minus 1, and y of t equals u of t minus u of t minus 1. Using the distributive property, we expand the convolution into 4 terms. Applying our general formula, u of t minus a convolved with u of t minus b equals r of t minus a plus b to each term, we get z of t equals r of t plus 1 minus r of t minus r of t minus 1 plus r of t minus 2. Both methods give identical results, confirming our graphical answer. Today we learned the general formula for shifted step convolution. U of t minus a convolved with u of t minus b equals r of t minus a plus b. We mastered graphical convolution. Flip one signal, slide it across the other, and integrate the overlap at each position. We worked through a complete example with rectangular pulses, identifying 5 distinct time regions. The algebraic method using distributive property provides an alternative verification approach. In the next lesson, we'll explore energy, power, and RMS for both discrete and continuous time signals.